Good day, I am Jürgen and I'm going to present topic 15, Digital Elevation Models. The contents of my presentation will be the following. I start off with a short presentation on how to obtain elevation data before I move on to different models to store terrain data. Thereby, I talk about conversion between data models before I finish off with talking about some operations and computations on terrain data, and also some applications where digital elevation models can be used at the end. There exist different methods and instruments for obtaining elevation data. Due to the amount of time, I won't go into detail in any of these, but it can be useful to know about them. LiDAR is a method that measures the distance to the Earth's surface using laser. Another method is using photogrammetry that takes aerial pictures. And a third method is topographic maps that are height maps with contour lines, as one can see on the picture to the right. And I will now go into more detail about the models that can be used to store this elevation data obtained by, for example, these three examples here. The regular square grid model is the first model that I want to talk about. It is a raster-based model that is stored as a 2D array in computers. Every element in the array has a corresponding elevation value. The element values can be considered as the value of the whole square, as the average value in the square, or as the value of just the center of the square. In the last two cases, one has to use interpolation in order to obtain the elevation values of every point in the square. This interpolation can be done by using a weighted average based on the values of the adjacent elements. Advantages of this model are: it is easy to model, and obtained elevation data often comes as a regular square grid. It is also easy to analyze due to simple interpolation operations on the array. Disadvantages of this model are: it requires a lot of memory, which may lead to slow algorithms. Because every cell has equal size, this may lead to a lot of redundancy in cases where a lot of the terrain has equal elevation. The next model I'm going to talk about is the contour line model, which is a vector-based model. One can often see this in height maps of mountains, for instance. The way to store this in a computer is by storing a set of contour lines along with the respective elevation value. One line is stored with a sequence of x and y coordinates, which then represents a simple polygon. In order to find the elevation of points that are not lying on the contour lines, one has to use interpolation. This is usually based on a point bounding contour line. The model can be stored in a D-cell, as we've seen before, or in a contour tree. In the contour tree, every node represents a contour line, and if two nodes are connected by an arc, it means that these two contour lines bound the same region. An advantage with the contour line model is that it can be used directly when digitizing a paper map with contour lines. A disadvantage is that it is not very useful without any further interpretation. The last model I'm going to talk about is the TIN model, which stands for Triangulated Irregular Network, and it consists of a finite set of points that are stored with their respective elevation value. A Delaunay triangulation is given for these points, which makes sure that everywhere in the TIN there are points that are lying on either vertex, an edge, or in a triangle. And this makes it easy to calculate the elevation values in all of the domain by using interpolation. If one wants the elevation value of a point lying on an edge, one simply interpolates the value of the two adjacent vertices to the edge, whilst in a triangle, one does the same but with the three vertices of the triangle instead. This model can be stored in a D-cell structure or in an object-based structure, which can be seen on the illustration to the right. Advantages of the TIN model are: it needs less memory due to the fact that the points are not uniformly distributed as they were in the regular grid model, and therefore only the most necessary points can be stored, which leads to faster computations and processing. And the disadvantage about TIN is the more complicated data structure. One needs a bit more pre-processing than, for example, in the regular grid model. Now that we have seen some different models to store terrain data, I will show you some conversion methods between the different models. This is useful in order to easily use the data model that suits one's application the best. And the first one I'm going to show you is how to get from a simple point set to tin. And this is very straightforward for us. One simply has to triangulate the point set, as we have seen in the course. And with the use of Delaunay triangulation, one will get well-shaped triangles. The conversion of regular grid to tin is a special case of the former one. One makes a triangulation of the center points of every grid element, and after uses a method to choose what points that should be discarded and what points that should be kept. One method to choose this is by looking at the values of the adjacent points and assign an importance number based on the elevation values of the neighbors. And small differences in values gives a low importance number, while a big difference gives a high importance number. Therefore, only points that are of great importance are kept, and points with the same information will be discarded, which lead to minimizing the redundancy. The contour line model to tin conversion is an important one, because a lot of digital elevation data is obtained by digitizing a contour line map into the contour line model. And in order to triangulate the contour line data, one can see the dataset as a set where every region bounded by a contour line is a polygon with holes. Therefore, in order to triangulate these polygons with holes, one can use, for example, the constrained Delaunay algorithm. I won't go into detail on this due to the amount of time disposable. Now I'm going to talk a little bit about computations and operations on tin models. And I'm going to start out with addition and subtraction. And an application can be, for example, oil drilling, where you need to find the thickness of the different layers in the seabed in order to know how much must be drilled. And one can use terrain data of the different layers and subtract them by each other. And the method to do this is by using an overlay of two tin models. You can place the T2 on top of T1, which will lead to that faces have 3, 4, 5, or 6 edges that needs to be triangulated, which is trivial. And there are 3 cases of elevation nodes. You have the original vertices in T1, where you basically take the value from the vertices in T1 and add the interpolated value in that point of T2. You have the original vertex in T2, which is the same as above, just switch the roles. And you also have vertices made by the intersection of 2 edges, respectively in T1 and T2, where you need to find the interpolated value at this point from both T1 and T2 and add them together. And algorithms to be used for the overlay is, for example, the Guibas and Seidel algorithm. And into the right you can see an illustration of how this is done. The next operation I'm going to talk about is squaring and cubing. And an application where this can be used is in wind erosion. If one considers a digital terrain model, but instead of considering elevation values at each point, one instead considers wind velocity as the value. Particles on the Earth's surface can be lifted and transported due to wind erosion, and the lift capacity varies with the square of wind velocity, whilst the transportation capacity varies with the cube of wind velocity. And a method to do this is by introducing an error limit, because an immediate problem arises when wanting to cube or square a terrain. The square of a terrain t will be a piecewise quadratic function, whilst there only exists linear function in tins. Therefore, tins cannot represent the square of t without an error. We therefore have to present new points on the edges of the triangles, as seen on the illustration, and triangulate these points as well in order to get a low enough error. So, what can digital elevation data be used for? There are different applications that use this data, for example in landscape modeling. In the illustration to the right, one can see a height map of the Earth, where a white area corresponds to high elevation values. There are also many other applications, such as different visualization applications and in modeling of flood and drainage, for example. And here is my reference, which concludes my presentation. Thank you for your time. I hope you enjoyed it.